The paper titled, Chain's Stiffness Effect on the Vertical Segregation of Mixed Polymer Brushes in Selective Solvent, investigates the microstructure of binary polymer brushes in a selective solvent. The study focuses on the effect of chain stiffness on the vertical segregation of the brush components. The authors employ a numerical lattice self-consistent field approach to study the behavior of the brushes. The introduction begins by highlighting the importance of smart materials in nanotechnology, with a specific emphasis on smart surface coatings. Polymer brushes are identified as promising systems for creating such coatings due to their ability to adapt their properties to environmental changes. The introduction further mentions various applications of smart polymer coatings, including switch sensors, anti-fouling surfaces, drug delivery systems, and protein separations. The authors introduce the concept of binary polymer brushes, where two chemically distinct macromolecules are grafted onto a surface. These macromolecules can have different affinities for each other and/or for solvent molecules, leading to microphase segregation within the brush. The focus of the study is on brushes with vertical microsegregation, where one type of macromolecule is located near the grafting surface and the other forms the periphery of the brush. The introduction highlights the importance of understanding the behavior of mixed polymer brushes and the factors that influence their microstructure. The authors note that previous studies have mostly focused on brushes with chains of similar flexibility and have not explored the effects of chain stiffness on the segregation mechanism. The paper introduces the numerical lattice self-consistent field method as the computational approach used in the study. This method considers the interactions between the components of the brush and calculates the volume fraction distributions of the chains. The authors also mention the use of the Flory-Huggins parameter to describe the solvent selectivity and the Kuhn segment length to characterize chain stiffness. The introduction includes a summary of the paper's structure, highlighting the subsequent sections on the model and method, results and discussion, and conclusions. The authors conclude the introduction by acknowledging the limitations of their modeling approach and suggesting potential directions for future research. In summary, the introduction of the paper provides an overview of the importance of smart materials and introduces the concept of binary polymer brushes. It highlights the gap in previous research regarding the influence of chain stiffness on the segregation of mixed polymer brushes. The introduction also introduces the numerical lattice self-consistent field method as the computational approach used in the study and outlines the structure of the paper. Profiles of the polymer volume fractions and free ends distributions. In the case of both chains being flexible, the free ends of the shorter chains move towards the surface as chi increases, while the free ends of the longer chains move deeper into the brush. In the case of semi-rigid responsive chains and flexible non-responsive chains, the intermediate layer of shorter chains moves towards the grafting surface, and the longer chains collapse and form a dense layer near the surface. These results demonstrate that the selectivity of the solvent and the stiffness of the chains play a crucial role in determining the microstructure of the mixed polymer brush. The transition between different microstructures depends on the interplay between the solvent selectivity, the chain flexibility, and the grafting density of the chains. Shows the distribution profiles of the free ends of the chains in the mixed brush. The profiles exhibit similar behavior to the volume fraction profiles in. This scientific paper investigates the effect of chain stiffness on the vertical segregation of mixed polymer brushes in a selective solvent. The researchers used a numerical lattice self-consistent field approach to study the microstructure of binary polymer brushes. They varied the solvent selectivity for one type of chains, responsive chains, while keeping the other type, non-responsive chains, hydrophilic. They found that with an increase in the hydrophobicity of the responsive chains, a transition occurs between two two-layer microstructures. In the initial state, the ends of the longer responsive chains are located near the external surface of the brush, while the ends of the non-responsive chains are inside the brush. When the hydrophobicity of the responsive chains becomes high enough, a reversed two-layer microstructure is formed, with the ends of the non-responsive chains near the brush surface and the responsive chains collapsing on the brush bottom. The researchers also varied the stiffness parameter for one or both types of chains and studied its effect on the transition. They found that if only the stiffness of the responsive chains increases, an intermediate three-layer microstructure is formed. If both types of chains have the same stiffness, the transition occurs gradually without the formation of an intermediate layer. The researchers investigated the effect of the stiffness parameter on the critical value of the solvent selectivity corresponding to the transition point and the steepness of the transition. They also discussed the significance of their findings in the design of smart surface coatings and other applications. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.